Hello guys, welcome to another video. Today we're going to work on a couple of problems of topic 4. So let's jump straight to the paper and see the solutions. The first question here, we have simple harmonic motion and superposition of waves. So we have an object of mass m that is placed on a frictionless surface and attached to a light horizontal spring. The other end of the spring is fixed. The equilibrium position is at B. The direction B to C is taken to be positive. The object is released from position A and executes simple harmonic motion between the positions A and C. So this is the amplitude. 34a. Define simple harmonic motion. So this is one of the questions that you very often see, and I'm always saying to my students that these are the questions that they give you extra marks. You cannot lose questions based on definitions. So what do we have to say here? You see 2 marks. So we have to say that the force or the acceleration, either term it's fine, is proportional and in the opposite direction to the displacement from the equilibrium position or from the fixed point. So this phrase here, it will give you both marks. You have to state that it is proportional, and also you have to state the direction. That's why you have 2 marks here. And this one is one of the definitions that you usually see, so be sure that you know how to express simple harmonic motion in the correct way. Now 34b, it says, on the axis below, sketch a graph to show how the acceleration of the mass varies with displacement from the equilibrium position B. So what do we know about acceleration? We know that acceleration, it's given by this formula, minus omega squared times x. So you see that we have a negative sign. Also here in the definition it says it comes to the opposite direction from the displacement. If you see here in your graph, you go from B all the way to C, all the way back to A, and so on. So when you have maximum acceleration, based on this formula, your displacement, it's gonna be maximum as well, but of course with a negative sign. So the maximum acceleration, it will give you maximum negative displacement. So let's call it here minus A is the amplitude. So one point is here. When acceleration is 0, displacement is 0 as well. When acceleration is maximum but negative, then the displacement will be positive. So maximum negative acceleration, okay, somewhere here, then positive maximum displacement, let's call it A. So this is the line that it gives you the graph between the acceleration and displacement. And the next one, on your graph, label the points that correspond to the positions A, B, and C. So what we have here, based on the diagram here, B is the equilibrium position. So of course, it's 0 displacement, 0 acceleration. Now the other ends, A is in the negative direction, so you have a negative displacement, and C is to the positive direction, you have the positive displacement. So these are your points, A, B, and C. So let's call this A0 and minus A0, just to don't confuse with a point A here. 34c, it says, on the axis below, sketch a graph to show how the velocity of the mass varies with the time from the moment of release from A until the mass returns to A for the first time. So A is one of the extreme points. So you know the velocity at A, it will be 0. Then what is happening? It goes all the way to the right, so to the positive direction. So your velocity, it has to be positive, and it's gonna reach the maximum velocity somewhere here when it is at the equilibrium position. Then it's gonna move to point C. At point C, it's gonna stop again. It's the other extreme position. So it's gonna be 0, and then it's gonna go back again. It's gonna increase the velocity to the maximum value to pass through the point B, but now in the opposite direction. So you have the negative value for the velocity. Of course, you're gonna reach the maximum point, and then at point A, you're gonna stop again. And this is how the graph, it looks like from position A all the way back and forth to the same position. And at number 2, it says, on your graph, label the points that correspond to the positions A, B, and C. So what do we have here? We start from A, zero velocity, we go all the way to position B with a maximum positive velocity, all the way to C that the object stops, all the way back to B with a maximum negative velocity this time because we go in the negative direction, and again we reach the point A. So these are the labels that the label points that you need to place on your diagram. And the 34D, it says the period of oscillation is 0.20 seconds and the distance from A to B is 0.040 meters. So AB actually is the amplitude. Determine the maximum speed of the mass. The maximum speed, it will be given, of course, by the formula of omega times A. So what do you have here? You don't have omega, but you can find it because you have the period. Omega is 2 pi over t. So you do the math here, you find 31 radians per second. So your velocity, what it's gonna be? It's gonna be the omega 31 times the amplitude 0.04. If you do the math, you're going to find 1.3 meters per second. The next one, it says that the graph shows the variation with time of the displacement of an object undergoing simple harmonic motion. Number 1, 11A1, state the amplitude of the oscillation. Of course, here you have displacement and guess time, so you can easily see the amplitude, and it's all the way up here. Now here you have to be careful, you need to count correctly the squares. You see here it's 30, and you have 5 squares between 30 and 40, so each square is 2. So the amplitude for the one, it is 32 millimeters. Be careful with the units here, what you see. And number 2, it says calculate the frequency of the oscillation. So this is something very simple. We have displacement against time graph. So we can read the period from this kind of graph. Okay, be careful. The wavelength, it's written by the displacement and distance. The period is written by the displacement and time. So what you have here, you go for a full oscillation. Here is your point. Again, you have to be careful calculating these numbers. Here you're 150 and one more box, it's 10 for each box. So the period for your second part, it will be 160 milliseconds. Again, be careful with the units. So the period, of course, it's gonna be 1 over t. And if you do your calculations here, you're going to find 6.25 Hertz. Here again, we need 2 significant figures, so you need to round this one. So either 6.2, either 6.3 Hertz are acceptable here. Number 10, it says that the diagram shows 2 point sources of sound X and Y. Each source emits waves of wavelength 1.1 meters and amplitude A. Over the distance shown, any decrease in amplitude can be neglected. The 2 sources vibrate in phase. Now points O and P are on a line 4 meters from the line connecting X and Y. O is opposite the midpoint of XY and P is 0.75 meters from O. Number 1, explain why the intensity of the sound at O is 4A squared. The O point is at exact same distance from X and Y. So the path difference is 0 between these sources. So if you have 0 path difference from X and Y, you have constructive interference. So this, it will give you an amplitude, a new amplitude of the addition of the 2 individual amplitudes, so 2A. So you know also that the intensity is directly proportional with the amplitude squared. So your new intensity that you are looking for, it will be equal with a new amplitude square, so that means it is 2A squared, so it gives you 4A squared. And this is what you want to prove. And number 2, it says deduce that no sound is detected at P. So at this point here at P, we have to see that there is no sound. In order to do that, you need to prove that you have destructive interference. And how you're going to prove that? By showing what is the path difference relationship with wavelength. From the x, the distance that the sound is gonna cross, it's gonna be all the way here. And from y, the distance is gonna be all the way here. So you need to calculate now these paths. How you will do that? Using Pythagoras theorem. This is your triangles that you want to work on. So you have this distance from O to P. So you're gonna find the distance of x, of the source x. What's gonna be? It's gonna be the square root of the one leg, 1.6 plus 0.75 square, plus the other leg, that is 4 square. So this is your one leg, and this is your other leg. So if you do the calculations here, you're going to find a number of 4.64 meters. Now the distance from y, what's gonna be? The one leg, that is 4 as well, and the other leg, that is this one here. So it is the square root of 1.6 minus 0.75 now, square plus 4 square. And doing these calculations here, you're going to find a number of 4.09 meters. So your path difference now, based on that, it is 4.64 minus 4.09, so it's 0.55 meters. Now the wavelength, it says at the beginning, the wavelength is 1.1 meters. So the path difference for you is lambda over 2. So that means destructive interference. And this is how you prove that you have zero sound at point P. 40b. Light of intensity I0 is incident on a polarizer. The transmission axis of the polarizer is vertical, you can see it here. The polarizer is rotated by an angle theta about the direction of the incident light. The intensity of the transmitted light is measured for various angles theta. On the below axis, we need to graph the intensity with the angle theta of the incident light when you have a light that is horizontally polarized and when you have a light that is unpolarized. So what is happening when you have horizontal polarized light? It means that it comes with this direction. So when it will be incident initially with 0 degrees angle in a vertical axis of the polarizer, of course you will see no intensity. So you reach the 0 intensity at the beginning. When you have the rotation in 90 degrees, that is going to give you horizontal axis of polarization, of course you're going to have maximum intensity at this point. So it goes all the way up, and then of course when you have 180 degrees, again it's going to be 0, your intensity. So it goes all the way down like so. Now when you have unpolarized light, it first incident in the polarizer, then the intensity of I0 over 2, the half of it passes through the polarizer. And of course it's going to be constant for the whole time. It doesn't matter of the angle of rotation. Now 41a. The diagram shows an organ pipe that is open at both ends. The pipe is emitting its lowest frequency note. On the diagram above, sketch a representation of the standing wave set up in the pipe. So we have the lowest frequency note, so we are in the first harmonic. So we have to create here the first harmonic. We have two open ends, so that means that these points here, they will oscillate all the way up and down, and here as well. So how it's gonna look? Of course, something like that. And this is the first harmonic of a standing wave in a pipe that is open at both ends. Label with letter P the point or points within the pipe where the air pressure is maximum. When we have maximum pressure, of course we have zero motion of the molecules inside there. So what we're looking for? We are looking for the position that it doesn't move at all. So here is your position B. And number 3, label with the letter A the displacement antinodes. So antinodes are the points that they move all the way up and down with a maximum amplitude. So what do you have here? Of course, here is your A, it goes all the way up and down, and as well here is your A, that it does the exact same motion. Now the next question is about standing waves as well. The diagram shows an arrangement used to produce a standing wave on a stretched string of length 2.4 meters. A standing wave with 5 loops appears when the frequency of the oscillator is set to 150 Hz, as shown below. 58. State the name given to point X on the string. So you see here that X is at this point, and this is the point that it doesn't move at all. So pretty simple, one word is just a node. 15b, 1. Calculate the speed of the wave along the string. Now in order to calculate the speed of the wave, we have the frequency of the oscillation, and also we need to find the wavelength. Now in order to find the wavelength, what we can do here is to see how many wavelengths we have here, and you see that you have 2.5 wavelengths. And these 2.5 wavelengths, they fit at a string of length 2.4 meters. So for the number 1 here, at 2.4 meters, you have 2.5 wavelengths. So you solve here for lambda, and what do you find? 0.96 meters. So this is the wavelength of your wave. So in order to find out the velocity, what you have to do, of course, V is equal lambda times F. So you have the wavelength, you have the frequency it says is 150 Hz. You just do the math here, you're going to find 144 meters per second. And number 2, it says calculate the frequency of the oscillator that will produce a standing wave with 2 loops on this string. So if you have 2 loops on the string here, you will have of course 1 full wavelength on your string. So your new wavelength, it will be the total length of the string, 2.4 meters. Okay, be careful here. 2 loops, 1 and 2 loops. So this is 1 full wavelength. So now we want to calculate the frequency. Okay, so the new frequency, of course, it will be given by this formula, lambda times F. But now we have a new wavelength that we're going to use. We're going to calculate a new frequency. Of course, the velocity, it's not going to change. It's going to stay the same. So the frequency, it's going to be V over lambda prime. So if you do the math here, you're going to find a number of 60 Hz. And this is your new frequency. 16a, it's a question about polarized light. An analyzer is used with polarized light. Outline the function of an analyzer in this content. When you have a polarized light, you need to cross the polarized light with the analyzer, and then after that you can determine the angle of polarization. So by crossing an analyzer with polarized light, then you can determine the angle of polarization. So the angle of polarization can be determined. And last one, 16b, polarized light of intensity I0 is incident on the analyzer. Number 1, the transmission axis of the analyzer is at an angle of 25 degrees to the electric field of the polarized light. Calculate in terms of I0 the intensity of the light that leaves the analyzer. So for number 1 here, what you have to do, you get your new intensity, that it's going to be, of course, from Malou's law, I0 cos square theta. Okay, we want to express this under the term of I0, but you have the angle. So what is it here? I0 cos square of 25 degrees. So if you do this calculation here, it will give you 0.82 I0. And this is your new intensity. And then number 2, it says the angle theta between the transition axis of the analyzer and the electric field of the polarized light is varied. On the axis, sketch a graph to show the variation with angle theta of the intensity of the light leaving the analyzer. So we see here that the specific intensity that is incident on the analyzer after a rotation of 180 degrees it's gonna, of course, reduce your intensity, it's gonna reach the zero, and then of course it's gonna increase it to its maximum level at 180 degrees. So this is how the graph should look like. So that's all for today, guys. Quite interesting topic. Sometimes we can find difficult things, sometimes not so much, but anyway, you need to study hard, and good luck.